In this video we're going to review implicit differentiation, and we're also then going to, with that, talk about the second derivative test. First of all, finding the derivative of something that is defined implicitly. Remember, implicit means that you can't get a y equals. Explicit is when you can get a y equals and you just find the derivative using the old rules. But of course, we can't just get a y equals out of this. So the first thing I want you to notice is that, we've got a product here, x squared multiplied by y. So we got to use product rule. First times derivative of the second, derivative of y is dy dx, plus the second multiplied by derivative of the first, which is just 2x. Derivative of y squared is 2y dy dx, and the derivative of 2x is 2. Now, the reason we always put that dy dx there is really chain rule. We've talked about that earlier, so I don't want to spend too much time on it, but essentially, think back in chain rule. When we had some function squared, we found the derivative by bringing the 2 down front, leaving the inside alone, dropping the power, and then multiplying by the derivative of the power, right? The derivative of that box would be 2 times the box to the first times the derivative of the box, I guess with respect to x or something like that. That's really what we've done here, is we treated y as a function. We dropped the 2 out front, dropped the power by 1, and then multiplied by the derivative of the function. So now we get the dy dx stuff on one side and the non-dy dx stuff on the other. So here I could subtract 2xy. Then on the dy dx stuff, I factor dy dx out. I'm left with x squared plus 2y. That's equal to 2 minus 2xy. And then we divide both sides by x squared plus 2y. This is my derivative. Okay, so hopefully you remember finding the derivative implicitly. Okay, we have done the first derivative test quite extensively. The first derivative test simply is when we find the derivative, locate the critical points, and use a number line to classify those critical points as maximums, minimums, or neither, using the derivative to tell when a function is increasing or decreasing. Today I really want to talk about the second derivative test and give you an example of when the second derivative test is really going to be the way to go. First of all, we all know what x squared looks like. It is a parabola. We know it has a minimum. I want to show you how the second derivative test would bear that out. So the first derivative here would be 2x. And a critical point, remember, critical points are where the derivative is either 0 or undefined. Well, our only critical point here is 0, because when x is 0, that would make the derivative 0. Okay. Now at this point, normally, we would have made a little number line and put 0 on it and done some work with that. I'm going to skip that for a moment, and I'm going to do what's called the second derivative test. So let me go down here. The second derivative, of course, is just 2. It's just positive, always positive. And because it's just 2, I don't probably need to do this, but I want you to think about, if I plug the critical point, I'm just going to put CP for critical point, or any point in, I'll get 2. Now the second derivative being positive means the original function is concave up. And because it's just 2, the original function is always concave up. Okay? So we have a critical point that could be a maximum or a minimum. And the original graph is always concave up. So think about something being concave up. If I tell you there's a maximum or a minimum and the graph is concave up, there must be a minimum. Because there's no way to have a graph be concave up and have a maximum. That's the second derivative test. That's it. It's using the concavity of the graph to classify maximums or minimums. Okay, now if you go back up to our first derivative test, and you say, well, Pick a number less than 0, 2 times that number is negative. Pick a number greater than 0, 2 times that number is positive. Of course, derivative is negative, then positive, so the function was decreasing, then increasing. It is definitely a minimum. Okay, let's go to the next one. F prime, of course, it's negative 2x. So f double prime is negative 2. Now, of course, the critical point is once again 0. Critical point is 0. So if I plug that in, again, I'm just going to put critical point. I know that's silly. I should be putting 0, but I just, for the sake of you remembering, that's what we're doing. We're evaluating at the critical point. We just get negative 2. Well, if I tell you the second derivative is negative, that means that the function is concave down. So once again, we rely on our concavity. We say there's a critical point, could be a maximum or minimum. The graph is concave down, so it has a shape kind of like this. Well, if it has that shape, it has to have a maximum. Okay. Now the last one, x cubed. Well, here, the derivative, of course, is 3x squared. So the critical point, bx equals 0. I'll leave a little room there. The second derivative is 6x. So when I evaluate the second derivative at that critical point, I get 0. Now it's tempting to look back at this and say, well, here I got a positive, so it's concave up. Here I got a negative, so it's concave down. Here I get 0. This was a minimum, this was a maximum, this must be neither. We don't know. This is what's called an inconclusive test. Okay. Meaning, we have to go back up and do our number line for the first derivative. Now, in fact, we all know what x cubed looks like. It is neither. But it won't always be neither just because the second derivative test fails. A great example of that is x to the fourth. X to the fourth, the derivative is 4x cubed. The derivative has a critical point of 0. The second derivative would also be 0, but x to the fourth has a minimum. So this is inconclusive. It means we have to go back to the first derivative test. Now, most people, when they see this, they would say, well, if the first derivative test always gives me the answer and the second derivative test doesn't, why would I ever use the second derivative test? Why wouldn't I just stay with what I knew and what I was good at, using the number line? For equations like this, I agree. I would do what I used to do. Let me show you an example where we'll have to use the second derivative test. So our first problem of the day, where we found the derivative implicitly. This is one where I don't think we would be able to use a number line. Okay, but let's look. Of course, critical points are where the derivative is 0 or undefined. Okay, derivative equals 0 or is undefined. Now, I'm going to focus on equal to 0 just in the interest of time. So where the derivative is 0 is whenever the numerator is equal to 0. Okay? If the denominator were 0, of course, that would make it undefined. It would be a vertical tangent instead of a horizontal. But I'm going to focus on making the numerator 0 for now. So I'm going to use a little algebra here, kind of quickly. So 2 over 2x is equal to y. That means that 1 over x is equal to y. Now, it would have been really nice here to get an actual number, to be able to say, oh, x is 2. That's a critical point because it makes the derivative 0. We're not at that point yet. We got a new equation. So what we need to do is see when our relationship, when 1 over x equals y, is true in the original equation. So I'm going to use the original equation right over here, and every time I see a y, I'm going to substitute in 1 over x. Like that. Okay. Now the nice thing is this gets me down to one variable. X squared multiplied by 1 over x is x. 1 over x squared is 1 over x squared. Equals 2x. Going to get some things together. Subtract x over here. 2x minus x is just x. Okay. Maybe multiply both sides by x squared. So I've got 1 equals x cubed. So x has to be 1. Okay. X has to be 1. Now we go over here and we say, well, okay, I know what x is, but this is a implicit. It's really important to know what y is. Well, again, we use our little relationship here. Remember that y is equal to 1 over x, so 1 over 1 is 1. So that's our y value. So the point 1, 1 is important. But how would I put that on a number line in this example? I don't know how. So what I need to do is use the second derivative test. Okay? Let me do that on the next slide. Remember the point 1, 1. So let me find the second derivative. Okay? Got low d high. Okay, so we would need to use product rule, of course. So there's low d high minus high d low cross the line and square the low. Okay. Now, at this point, we want to evaluate at the critical point. Okay, I'm going to put a little line here like this. That means evaluate at the critical point. Well, remember, we know that x was 1. We know that y is 1. And the one other thing you see here is dy dx. Right? That appears a couple of times. Well, remember, we designed this so that the derivative was 0. That's what we solved for. dy dx is equal to 0. So we start plugging that in. 1 squared plus 2 times 1, it's 3. Negative 2 times 1 times 0 minus 2 times 1 is negative 2. Over here, 2 minus 2 times 1, this whole thing, 1 times 1, this whole thing is 0. 2 times 1 plus 2 times 0 is 2. And the bottom, 1 squared plus 2 times 1 is 3. 3 squared is 9. So if you actually did it, we have negative 6 minus 0 over 9. We get negative 6 ninths. So the second derivative is negative. Okay, when we plug in the critical point to the second derivative, we get a negative, meaning the original graph is concave down at the critical point. Now concave down, remember the shape, concave down, that must make that critical point, this critical point, a maximum. And you can see that by the graph. I put that in here, that 1, 1 is indeed a maximum. This is the case where you would need to use the second derivative test. You don't have a choice. There's no number line stuff you can do on this. You have to actually use the second derivative. Implicits are a great example of why it's so valuable to remember that we can use concavity to classify maxes and mins.